All right, thank you. Yeah, as was said, my name is AJ Gemmer. I'm the Chief Technology Officer at Lunar Outpost, headquartered in Golden, Colorado. And I'll be speaking today on our surface mission Conops Planning tool, which we call Cosmos. So at our core, Lunar Outpost is a space tech company that creates fully autonomous robotics for extreme environments. In this context, that means the lunar surface from the equators to the poles and potentially in the future even into permanently shadowed regions. So we envisioned creating rovers that could be deployed rapidly and frequently and providing a rover for every PI and every instrument. To that end, here's our current rover lineup. On the left, we've got our Mission 1 Mobile Autonomous Prospecting Platform, or MAP, and you can see a version of that in between the doors to the central ballroom there. But that's about a 12 to 20 kilogram rover, which supports a single lunar day mission. Also in the works is our Lunar Night Survival Rover, which we call Cold Map, about the same size, a little bit heavier because of its thermal control system mass, but we've integrated a number of mature thermal control technologies into that rover, and we're prepared to send that one for flight as early as this year. And then, of course, looking to the future, we're looking at larger rovers in the 100 to 300 kilogram class, and we call that our heavy lift map, shown there on the right. And on the far right, you can see sort of a hint as to what we see of the future of rover products. And I always like to show this slide. It's cool to see renderings, but this is actual spaceflight hardware that we have in our labs and in testing, everything from dusty thermal vacuum testing to outdoor testing, which provides a lot of variability in the environmental conditions. It's quite challenging, as well as traditional flight qualification testing like shock and vibe, and functional testing like deployment from our lander deployment mechanisms. Which brings me to the Conops planning. So I'm happy that I got to present last because some of the science objectives like Eldar and Sherry presented are, of course, at the forefront of the objectives for our mission. But in order to gather those data products, we need to take a number of other considerations into account. Things like our communications availability and bandwidth, both for command and control data for the rover, as well as for our science data, which can occupy a substantial portion of that bandwidth. We also need to take into account the rover's interactions with the lunar environment, things like the local terrain, the slope, slip and sinkage in regolith, and the thermal control of the rover, which of course is influenced both by the lunar surface and by the solar illumination. And as our rovers are currently solar powered, the solar illumination also dictates how much electrical power we'll have for driving and for operating our science instruments. This Conops is also subject to a number of constraints, a big one being that all of our a priori path planning is currently limited to a maximum resolution of about 2 meters per pixel from the LROC narrow angle camera. So given that our rovers are only about a half meter in length, there could be substantial obstacles hiding in a single pixel of that data. Still, we need to have a preliminary plan before we launch. As I mentioned, the interactions of the hardware with the lunar environment, especially if they are not as analyzed or if things seem to be changing rapidly in the mission. But most of all, time. Compared to past Mars rovers missions, these lunar missions of a single lunar day are extremely fast. So we need to be able to make decisions very quickly, adapt to new information and new data as it comes in, and upload a new path and create a new Conops and a new plan really on the fly. So we developed what we call the Cosmos ground station. This is how we operate our rovers. So it provides our operators with the telemetry data, things like comms bandwidth, power, and thermal conditions, and allows the operators to send commands up to the rover, uplinking new waypoints and drive paths. At the same time, this is a web-based interface that our science team can log in from wherever they are. So it provides the science team with the tools that they need to analyze or to at least get a first look at their science data and evaluate if we're meeting those science objectives that we set out to do. A side effect of this is because we designed this to be rapidly iterative, it helps at the proposal stage when we need to develop sort of a sample or a proposed Conops given a limited amount of information. So other payloads, it provides those payload customers the capability to interact with their payload or instruments, send it commands, downlink data in various forms. And of course, we need this to be secure and secure all of this data that's coming down from the rover itself. So I mentioned the 2 meter per pixel digital terrain maps. As I said, we send the rover. Rover launches with some sort of preliminary Conops and waypoints already loaded on it. But as the lander comes in, it will generate a new digital terrain map of much higher resolution. And we expect to have access to that within the first few hours after landings. So when that new digital terrain map is downlinked, we pull it into Cosmos and process it. And perhaps with this new high resolution, we see, okay, we need to move a few of our waypoints. So the graphic here on the left shows the red waypoint. That's a point that we've already reached. The 3 green waypoints are ones that are in the planning stage, which we are tweaking. And the blue ones are future waypoints that were the defaults uploaded when the rover launched. So once we have evaluated that, tweaked our waypoints, we can run a simulation and output, like I said, the power, comms, and expected values for our new traverse. If we like that, we uplink our new waypoints to map. And as map drives, it will also be creating higher fidelity digital terrain maps. So once we get outside of that area that was covered by the lander, we will still be receiving new terrain information and performing this iterative process over and over as we drive. So the outputs of this at each stage, each analysis, are the input powers to our PV arrays based on the local solar vector, the motor power, which is based on the elevation, gain, and loss from the terrain, our attitude in roll, pitch, and yaw, similarly dictated by the terrain, and the time and date between the waypoints that we uploaded. And I should clarify, these waypoints could be quite far apart, in which case we would want to use Autonomy to navigate between them, or they could be spaced very closely together if we want to have essentially teleoperation control of the rover. So our waypoints can be calculated in 2 different ways: a forward calculation, where we calculate the time that is required to reach each waypoint, assuming that we can maintain some sort of average speed. But we could also do a backwards calculation, where we calculate the average speed which we must maintain in order to reach a waypoint at a certain time. And this matters, for example, in a polar mission, where you want to be at a certain point on the terrain when the sun is at a certain angle or certain position in the sky to maximize your electrical power. We can also output the RF comms propagation over the terrain and balance that against the science objective so that we can stay within an area of optimum communications. And so this gives an image of what our dashboard looks like when you're driving the rover. So you can see on the left there, got our battery percentage remaining, our current speed, power being consumed, and our comms signal strength. Along the bottom, you have historical navigation camera data, so you can go back and review an image quickly. And then on the right, this would be essentially a teleoperation setting. And so, this is how we can command the rover and basically drive it in real time or near real time. We have a number of other dashboards in Cosmos as well. So these are plots of our power and kinematic data as we drove. When we do that simulation step in the iterative process that I described, we can plot these out, what we expect these values to be through the mission, and then overlay them on the actual values and see if our simulation seems to be diverging greatly from our expected values, in which case we can stop, reevaluate, and upload a new set of waypoints. And finally, I mentioned the thermal data as well. So this interaction with the lunar surface is one that's not very well quantified. And so again, we will perform our thermal analysis to the best of our ability before the mission and plot out what we expect our temperatures of various areas on the rover, say the front top and front bottom panels throughout the mission. And then we have thermal sensors on those panels, and we will plot the actual temperatures. So again, if we see, well, we expected that we would be cooling off during this time, but actually we're heating up, that tells us that we need to do something to address that, either control the thermal analysis or the thermal management system, change the orientation of the rover, stop and enter a hibernation state to cool down, something like that. So it gives us that sort of real-time feedback and allows us to make those decisions very quickly. And so with that, I'll open it up to questions. Thanks for having me.
Great.